So if we have a look at that column.
Designing Randselva Bridge, the challenge was the river and the very unstable masses on the western part of the river. So we didn't want to touch those masses at all. And in the middle there's a valley, so you don't want your motorway to be too steep. So we ended up with a design that was 634 meters long, crossing the river, crossing some unstable masses, 2 roads and a railroad.
The construction industry has been slow to adapt to BIM for several reasons. The main reason being that you only do one of each type of construction, and then you move on to something completely different.
This is a completely new way of working, not only because of the modeling itself in 3D, but also because of the information you can include in the models and how you provide the information, not only for the construction itself, but all the suppliers involved in the construction of bridges. And this is, I think, the key to success in Norway, is that every company strongly believes that this will make a difference in the future.
So we can see spacing, it's constant all along, but then you have each 200 millimeters, you have different rebars, so you change colors so that they can identify more easily what is the 100 millimeter spacing or 200 millimeter spacing.
Even though we are in different countries, because we are based in Portugal and Sweco is based in Norway, with shared models, and also using colleagues from Sweco in other countries like Denmark, Poland and Finland, all modeling meetings were done in a unique common environment. Yes, the software is fully prepared to do this type of technology, because it separates the objects in a way that we can reuse them whenever we want and how we want to use them. And all the properties can be included in the objects. Extra information like the cover for the concrete, materials used, inspection criteria, and other different types of information.
It's a bridge that has a very complex geometry and very few 90-degree angles. Trying to represent that with a 2D drawing is very hard. You end up making loads of sections, and that section is only valid for a very small area. So with a 3D model, instead of drawings, you're able to transfer information on very complex geometry to people building it in a far superior way than you would with 2D drawings.
Yes, due to the complexity of the bridge, it's a curved bridge with variable heights all along of the bridge. So we needed to use parametric design so that all of the variations that were used not only for geometry but also for the reinforcement were much more easy to assemble in the model and much more productive when building the full model.
Parametric design is basically setting up computer rules to do the design for you. So say on a bridge project you have a road line. One rule can be that every 2 meters you need a railing post. If the road line changes, the computer rule understands that and can place your rail posts in another position. So the next rule could be that every 20 meters you need a light pole, and yet then you keep on adding these rules. And if you do that well enough, then you can basically make any design repetitive in another position as long as you have a road line. This is better done when you have repetition. So if you have a bridge like Randselva Bridge, that's 634 meters long, then you'll have a lot of repetition in many places. What we did was setting up these rules, especially for reinforcing the bridge. Because in the BIM model we have well over 200,000 rebars. We were able to model maybe 70% of these parametric. Well over 100,000 rebars were positioned automatically. We set up some rules, a computer does the rest.
When people drive over it, I don't think they ever think about these things, but underneath them is a super complex structure that took many experts and many pioneers to build. The people at site doing this was one of the first in the world that ever did this.